Hey everyone. So for this video, I'm gonna keep it really short. There's just like the last little thing I wanted to make about the gases chapter, just because I never learned this really like in AP Chem or College Chem. We never talked about effusion or diffusion. I know some people do, so I want to make this video just in case to cover like any questions you might have. They're both very similar, and honestly, like out of all the chem things up until now for gases, like probably the most straightforward. Like you really can't get many questions outside of just like the two equations you need over this and literally do the same equation basically. So like don't worry about it. And I'm gonna show you like a dumb way to remember what these both mean. So like don't even, this will be a very quick video. Like you'll be fine. I promise. But yeah, let's just like jump into it. So for effusion, basically all effusion is, I say effusion, that's my preference. It's just gas when you put it into a chamber and you make a little hole in it and let the gas pass through. Now, technically, the rigorous definition of effusion means it's going into a vacuum. So it means there's no pressure on this side of the chamber. So all the gas wants to flow in one direction out of the chamber and not flow back. Um, Outside of that too, like I think the only other major thing about effusion is that the hole is like so small that oh geez, the hole is so small that only one gas particle can flow out at a time. Which like you'll see like a minor difference between them. It's important to know. So for effusion, one gas particle comes out at a time. So as you can imagine, smaller particles will be able to flow out faster and more quickly, like in less time. And yeah, like basically the way we talk about this is that we're always comparing two gas particles since who cares how fast one gas flows out of it? You can just track that. But if you want to compare two gases, you basically just say that the rate for gas one compared to the rate for gas two. Gas one and gas two are arbitrary. It's whatever you want to define as your gas one and your gas two. All that matters is that be consistent with your one and your two. Because you'll see in the rest of this, like those one and two are what determines like what's the numerator and what's the denominator. So just write that out really clearly when you want to start problems like this. So this rate, like we talked about in the last video with the Boltzmann distribution, this is just going to be your root mean squared, which I'm going to keep saying because like I think it's very important for everyone to know the difference between like velocity and root mean squared velocity. Really, it's the same thing for most cases, but like I think it's just a good thing to be aware of. Um, so these rates, and now in terms of like I think I'll give you the equation and then I'll show you where it comes from instead. So these rates, so the rate of whatever arbitrary gas one you pick, divided by the rate of gas two, will be equal to the ratio then of the mass of gas two divided by the mass of gas one. So this is where I said you really got to keep your ones and your twos straight because they get flipped, right? It's kind of weird, but like if you want a good way to remember this, just think about it like this. It's a simple fact that this left side of the equation, so right here, all of this stuff, it tells you how much faster is gas one than gas two. Faster is gas one than gas two, right? Because if gas one moves twice as fast, this will just be a two because it's double, right? Um, and then if you want to compare that to the right side, I think that's what's important to keep in mind. Like, think about like this. If two gases have the same energy, right? I'm going to keep iterating this from the last video. Same energy means the same temperature. We're going to always say that. If you're at the same temperature, you have the same energy, they what's going to make a gas move faster, do you think? If it's a huge big molecule trying to fly around or a very small like hydrogen atom, right? If you want to compare it to like cars, think about like I don't know, like a pickup truck or like one of those like RV trailers, compared to like I don't know, a Ferrari or whatever. Like whatever is smaller will move faster. So if you want gas one to move faster, then gas two has to weigh more. So if gas one moves faster, gas 2 must weigh more. And again, it's not a huge deal. Like if when you get your answer, if you just ask yourself this question about gas one and gas two, um, that'll basically tell you if you did it right or not. And we'll do a practice problem right now as well. But just keep those ones and twos like straight and don't like I don't know. This is a pretty easy one where I, in my experience, for different examples, would like make my ratios like I would do them like mass one over mass two on accident, just 'cause I was going too fast. So just try to keep that in mind. Yeah, let's do a practice problem right now to show you this. So for this problem, we have what is the molecular weight of a gas that diffuses 1/60th times as fast as hydrogen? So for this, we're gonna just like think about the equation, right? So for the equation, we have the rate of gas one over the rate of gas two has to be equal to the square root of the mass of two over the mass of one, right? So we don't really have any information on the rate per se. All we know is that this, whatever gas this is diffusing 60 times slower or 1/60th as fast as hydrogen. So let's just make the math easy, right? If I know this is going 1/60th times as slow, I would just say that the rate of gas one, wow, gas one equals one, right? And then let's say that the rate of gas two is 60 then, right? If you don't know why I chose that, just think about the question itself. We know that we know that there is a gas that moves 60 times as slow as another gas. And we can pick whatever rate we want because remember, the units cancel out here. This is just a ratio. I could have said 2 and 120. I could have said 4 and 240. It doesn't matter because ultimately this goes into a ratio. So I can say that the gases move however fast that they're going to move, right? So long as the ratio between the gases matches the ratio I was given in the problem. So if you don't have information on the actual rate of the gases and you only know like relatively like, oh yeah, this gas moved like 4 times as fast or like 100 times as slow or whatever. Just pick numbers that make the math easy for you. That's like the best advice I can give. Is that if you have problems like this that are pretty unclear, just like make it as easy as possible for yourself. So we have that much. And so we can also look at the masses. We're trying to figure out the mass of one of these gases. So I would just say then, actually, one thing too, we know that one of our gases is hydrogen. And if you had to guess, do you think hydrogen is the heavier or the lighter one? I'll give you a hint. It is the lightest element on the periodic table. So there's nothing that can ever be lighter than hydrogen. So given that, it makes sense hydrogen will be the gas that moves the fastest. Again, whatever gas you call gas one and gas two does not matter so long as you're consistent with the masses, then that's the important thing. Because I already called gas two the one that moves at 60 and gas one the one that moves at 100. Sorry, the one that moves at one, right? I therefore need to be consistent with the mass then and say, what the heck? There we go. And say that hydrogen is one of these two. So hydrogen has to be the gas that's moving faster because it's the lightest one also. So it's going to be H. Okay, awesome. So we have that. What we're going to do now is we're actually going to figure out what the mass of this gas is. So we're going to set the ratio. So we know that 1 over 60, because this is the rate of gas 1 we said, and this is the rate of gas 2 that we said, has to equal the square root of, ooh, okay, M1, right? Because remember, it's flipped. I almost made a mistake. It's flipped. So because the hydrogen was here in the denominator, it goes up here in the numerator. It goes up here in the numerator. Now I left it blank for a reason because what do you think the mass of hydrogen should be? If you said one, You're very close, but just keep in mind that with gases, a lot of the times, if they're not noble gases, they're diatomics. So hydrogen doesn't exist as H. So H gas doesn't equal this in nature, where you don't see hydrogen as just a hydrogen atom or even as like a weird anionic species. You see H gas looks like this. It looks like a hydrogen with a single bond. So it's two hydrogen atoms bound together. The exact same thing is true if you look at fluorine, chlorine, all the halogens. Those all exist as diatomic elements. So the mass of hydrogen isn't going to be one, it's going to be two, because we have two hydrogen atoms bound together. All right, so we have that. Now we just want to just isolate what M1 is. So if we square both sides, we're going to get that 1 over 300, sorry, 3600, not 300. This has to be equal to 2 over M1. And then, let me think about what's the easiest. Yeah, just like, you just like do the math kind of. We multiply both sides by M1. So we get that M1 over 3600 has to equal 2. And then multiply both sides by 3600. Cancel that out. And so we get that M1 has to be equal to 7,200. A very big gas. I don't know what that could, it could be some weird compound. Maybe like a weird like no, well, it could be like a weird alkyl, like alcohol chain or a lipid. But that's basically the approach you want to have for these problems is just identifying like gas one and gas two based off however you want to do it. In this case, I did it based on the fact that we have the ratio of 1 over 60. We were given that and told that there is a gas that moves 60 times as slow or 1/60th as fast as hydrogen, meaning hydrogen has to be the lighter element here. So I said, okay, gas one, you move at 1/60, your hydrogen, you move 60 times as fast. Let's just do that. So it's really just a matter of doing whatever you think comes to mind first, or whatever makes most sense for you and how you solve problems. And yeah, that's basically all there is to effusion. It's just a fact that you have to keep in mind that the mass does matter absolutely, as you just saw, and how the mass impacts velocity. It's not linear. So if you give me two gases and one is 4 times as heavy as the other, it's not going to effuse 4 times as fast. It's going to effuse twice as fast because it's the square root of the ratio of the masses. So whenever you get a problem that's like, oh, you have all these gases, which one is going to effuse the fastest? It will absolutely be the one that is the lightest. It will be the lightest gas. Um, but that's not to say that it will effuse directly proportional to how much lighter it is. So if you look at like hydrogen and let's say helium, right? Hydrogen, as we just said, has a mass of 2. Helium has a mass of 4. That ratio, 4 over 2, is 2. That does not mean hydrogen diffuses twice as fast. It is the square root of 2 that we see here. Because it's the square root of the ratio of the masses. So hydrogen would diffuse root 2 times faster, or 1.414 times faster. Don't quote me on that. All that to say, look at your masses and then figure out that ratio. It'll be the root that tells you how much faster certain things are going to effuse out of the chamber. And yeah, that's basically it for effusion. I'm going to talk about diffusion really quick and then end this video. So diffusion is the exact same thing as effusion. It's almost the exact same thing. That's why the names are almost identical. What is different though is that with diffusion, it talks about how gases travel through a certain distance, right? Um, and I really should have, we'll add this here. I'll add this now. So if you have two gases in some chamber, right? And you open it and you allow the gas to just travel through it. Um, the difference here is that there's no small hole. The gas can travel as much as it wants, as there's nothing limiting what gas can go through first or anything like that. Um, so that's the basic, that's like the main difference. And with diffusion, we really don't look at the velocity or how quickly, um, like how quickly this is done. instead we look at the distance that this can travel. So you usually will say like, oh, in like 10 seconds, which gas will travel further or whatever. You usually give it time just to like, make it relevant for what you're talking about. And like the equation, it's almost identical. Basically, all you say is that the rate of gas one, so again, just like um, with effusion, we talk about the rate. But like I said, we're talking about distance now. So logically, what makes the most sense here is that if something travels faster, right? You even think about this like from physics when we talk about kinematics. When things travel faster, they travel a greater distance. And like I said, we talk about this all in the same amount of time, in 10 seconds, 20 seconds, maybe a minute, or like an hour even. In that time, who travels further? Well, it'll be the gas that travels the fastest. So knowing that, it means that velocity and distance are related. It means that as velocity increases, so will the distance. So the distance of gas one over the distance of gas two will also be a similar ratio. It should be the same ratio even. And based on what we know from the previous part with effusion, I gave you the fact that the rate is equal to this ratio of m2 over m1. So the same thing is true down here. Oh, wow. I forgot to give you the reason as to where this comes from. Really quick, small aside. Go back to kinetic energy, right? This is using conservation of energy. So if we say that, let's say 1/2 m1 v1, actually, we'll do this, right? All I'm using here is conservation of energy to say that the system is at the same temperature, meaning that the kinetic energy of both gases will be the same. Doesn't mean they move at the same velocity, just means that they have the same energy at that moment. So because of that, we can set them equal to each other. So this is basically saying that kinetic energy of one has to equal the kinetic energy of two. And now we just simplify it. So this 1/2, it cancels out, multiply each side by two. And then we want to get that ratio of the rate of one over the rate of two. So we will divide both sides by u1 squared, canceling that. And then I'll divide both sides by m2. Oh, wait, no, that's wrong. Oh, come on, I was so close. I was so close. Let's divide both sides by u2, my bad. U2, because now we have this ratio here of u1 over u2, which is rate 1 over rate 2. That's what we want. Jeez. And then we'll divide both sides by m1. So now we get that u1 squared over u2 squared has to equal m2 over m1. Take the root, and bam, that's where you go. It's not important. Again, I'm just doing this to like talk a bit more and hear myself talk and just like show you where this comes from. But like it all of chemistry is just energy, energy conservation. Everything happens because it is favorable due to energy in some way or somehow. So that will come up in AP Chem and Gen Chem and O Chem and every chem you take. That's just what chemistry boils down to, right? And yeah, I'll just give you a quick practice problem with diffusion, and then that'll basically be it. So determine the rate of diffusion for water versus argon. I kept this one very, very short and simple. There can be other ones that are more complex where you're like, figure out the distance it travels, but like it doesn't really matter. Like you'll see what to do based on the problem, what it gives you. But yeah, if we want to do this, basically we just have to say that the rate of water over the rate of argon. This has to equal the root of the mass of argon over the mass of water. Um, my gosh, sorry. I was trying to think what the mass of argon was. So then take the root, and this will give you 40 over 18, which is 1.49. So what this would mean, it means that water will travel 1.49 times as further um, than argon will in the same amount of time. Because this, I forgot to write down, this is d water over d argon. So how can you see this? Let's say they tell you that they can tell you like how long the pipe is. So like they tell you it's like a 30 centimeter like pipe or container and say like 20 seconds, then you'll know the distance being 30 for both and the time for one of them. Or no, sorry, you would know the time for both of them, and you would know how much faster water is moving than argon. That lets you find the distance. Diffusion really doesn't come up all that often. It's very rarely ever taught. Just it's not that interesting really, but in case it ever, for whatever reason, appears in your syllabus or like in your class, like hopefully this gives you some context for how to think about diffusion and effusion. And yeah, if you have any questions, like feel free to like leave them in like the comments. I'll hopefully have the notes of this also upload so you can do it. Um, yeah, let me know if there's anything else I can do to like help out with this kind of stuff. But yeah, hopefully next I'll be going on to the equilibrium and the yeah, more of the reaction types of chemistry chapters. So looking forward to it. I think it'll be really fun to talk about. But yeah, thanks for watching. Hope you guys have a great day and yeah, enjoy the material.